Hi, my name is Kalei, and today I'll be going over the valence bond theory and the crystal field theories using. Now we need to determine the correct oxidation state of manganese ion. We already know that ammonium is neutral, nitrite has a -1 charge, and there's 3 of each. We also have an overall charge of -1, as you can see here, for this entire complex ion. So using some algebra, we figured out that manganese has +2 charge. We need to study the ligands of this complex ion. So ligands are Lewis bases, which donate pairs of electrons to a Lewis acid. The Lewis acid in this case would be the central atom, manganese. And as you can see, both the ammonium and the nitrite have a lone pair of electrons in order to donate to the manganese. It is also important to note that it is the nitrogen, in my specific case, that will be binding to the manganese, because both of these ligands are monodentate, so only one atom at a time will be binding to manganese. This is another visual of my ligands that I want to show you. So on the left will be your nitrate, and on the right is going to be ammonium. And they each have their pair of pair electrons to be donated. As I mentioned before, the nitrogens of each ligand will be binding to manganese 2+ by donating the lone pairs of electrons, and that will form an octahedral shape in which all angles are going to be 90 degrees. It is also important to note that nitrite is a monodentate. It also could form linkage isomers, so it doesn't have to bind to the nitrogen in all cases. And another isomer could actually have a link to the single bonded oxygen. Also, the ligands don't have to be in this specific order around the manganese. They could be scattered all around the manganese, but isomers could be another video for the future. Now we need to discuss whether these ligands are strong field or weak field. And you can tell by their placement on this spectrum line, as you can see here. So both ammonium and nitrite are on this stronger field ligand side of the spectrum. So we know that our species is going to be paired diamagnetically, in which it will try to fill its orbitals by pairing before filling up the rest of the orbitals. And I will demonstrate this by showing how an orbital with 4 electrons will be filling up these orbitals. 1, 2, 3, 4. As you can see, 4 electrons in a weak field ligand would take up 4 orbitals. In the strong field ligand case, we're going to be completely filling up 2 orbitals in the lowest state before moving up to the higher states, from the T2G to the EG. And that demonstrates what the larger delta, or the larger crystal field splitting, is, because it takes more energy to send an electron up to the EG level than it does for it to be paired up with another electron. And I'll be demonstrating how to produce an ion out of manganese 2+. So we always lose electrons from the lowest orbital, the 3s. So now we have a total of 5 orbitals in the 3D. Now that we have all that knowledge, we can now produce the valence bond theory of this complex ion. So I drew how the 5 orbitals appear in manganese. However, this doesn't demonstrate the diamagnetic property that we mentioned earlier. So we need to add pairing energy in order to pair the electrons. And because we are adding pairing energy, that takes manganese to an excited state. Now we need to hybridize unfilled orbitals after the last filled 3D orbital to bond the ligands. So because we have 6 ligands, I will be hybridizing 6 orbitals. So now we're going to correctly label this instead of D4S4P. We're going to just simplify this as D2 because we have hybridized 2D orbitals, and then SP3, 2D orbitals, 1s, and 3p orbitals. Now we could fill in the bonding to ligands. So here we have 3 2 minus sigma bonds. So drawing the electrons this way shows that our ligands are donating our pairs of electrons. And now this is going to be our bonded state. I'm going to confirm this theory using the crystal field theory. In this diagram, we're going to show the diamagnetic properties not in this part of the diagram, but rather in this area of the diagram. This diagram gives a visual of how the electrons pair up and then move up if given enough energy to move up from the T2G to the EG levels. But because we have a strong field ligand, it takes a lot of energy to move up these electrons from T2G to EG. So I'll be demonstrating this. And because we have an odd number of electrons, 5 electrons, that creates a diamagnetic spin. That actually creates a paramagnetic spinning. You also need to note that it takes more energy to split. So we know that it takes more energy to split than it does to pair up, because it is easier to pair up than it is to take energy to move up from an electron from the T2G to the EG. In summary, we know that this is paramagnetic because it has an odd number of electrons in the d orbitals. And now we know that this is a DSP3, and that is characteristic of a octahedral shape. And we already know that splitting energy is higher. Yes. And our ligands are strong field with the coordination number 6. Okay, thank you. I hope this video helps.